study looking at the internal evolution above redshift 3. So, but I mean, in this region, some of the theoretical studies expect those galaxies form stars everywhere. The quenching may not happen yet at that epoch. So the question in this study is that we're going to see how these massive galaxies grow at this redshift range and where stars form inside the galaxies. And we're going to see, looking for any indication of suppression of star formation at any radius. So in order to do that, we perform spatially resolved stellar population study for these galaxies above redshift 3 in order to compare star formation activity between galaxy inner regions and outer regions. Yeah. In order to do that, so we collect around 200 galaxies at the redshift ranging from 3.5 to 4 from a photometric redshift galaxy catalog from Finkelstein et al., which is based on the Kendall's data set. So now I'm using HFT and spatial IRAC photometric data, and also utilize the high spatial resolution ground-based KBN data from HiPACC survey. So in order to resolve this kind of a small nugget, small galaxies at high redshift, we really need a high spatial resolution. So I'm using the HFT image and KBN data, which has a very high spatial resolution, to measure the physical quantity for the spatially resolved regions. But the spatial resolution of the IRAC data is not enough, so I'm using it for the constraining the integrated property. So what I'm doing is that, so first measure the fluxes from galaxy inner region and measure fluxes, the rest part of the galaxies, considered as the outer region of the galaxy, and doing spatially resolved SED fitting based on MCMC algorithm. And then here's the listing of for a whole bunch of details for the modeling SED and fitting parameters. And now I'm get these physical quantities from both galaxy inner and outer regions. And then, as I mentioned, we are focusing on the comparison of specific star formation rate between two regions, galaxy inner region and outer region. And then our SED modeling already tested with the simulated galaxies, and then we confirmed that our SED modeling accurately recover this specific star formation rate when we have a KBN data which cover the optical wavelengths information of these galaxies. Yeah, and then this is the key figure of my analysis. So I measure the specific star formation rate ratio, which is the specific star formation SSFR from outer region divided by SSFR from inner regions. And then I want to see how this SSFR variation is correlated with these two physical quantities, which are considered as closely related to the galaxy quenching. So the first plot shows the relation between this ratio with the central mass density, and the bottom plot shows the ratio versus total stellar mass. And as you can see here, the individual data points are scattered a lot in a plot, so it's really hard to draw any relation. But so when I measure the correlation coefficients, which shows some linear relation, then I get some number, which means this has a moderate the linear relation between the two quantities with a high statistical significance. So I measure the slope of a linear fit, and then the slope is also have some positive relation with higher than 2 sigma significance. But we do not see such a relation in this bottom plot. So one conclusion from this analysis is that at redshift 4 galaxies, we see some moderate evidence for the galaxies with high central mass density are more likely to have suppressed the star formation rate in the centers. But this quantity is not really depends on total stellar mass yet. Yeah, so far I described some results from my SAD fitting, but it still depends on the galaxy model SAD. So we want to see some direct observables like galaxy color. So here I measure some stacked color variation between inner and outer regions inside the galaxies. This color, J-K color, represents the 4,000 angstrom Balmer break, which is sensitive to age evolution, and this I-G color shows UV slope, which is sensitive to dust extinction. And then I measure the stacked color from two different groups. So the first group with a blue dot, which is measured from the galaxies which have a similar specific star formation rate from inner and outer region. And the red dot shows the galaxies which show a relatively lower specific star formation rate in the center. And as you can see here, when you see the red dot, then the color changes the redder in J-K color. That means in these galaxies have a relatively older stellar population in the centers. But we do not see such a large color variation in this group. So from these color changes, we also find some similar findings, which is pretty much consistent to what we found from the SAD fitting that I showed the previous slide. And so far, I presented about the result about the redshift 4 galaxy, but we also try to do this kind of analysis up to redshift 6 because we have those data. And then, but I would note that in this analysis, actually the K-band data is not helpful anymore to constrain stellar mass better anymore. So I'm not using K-band data in here, but take advantage with a better resolution from HST images, which has the finer spatial resolution than the K-band data. So my bidding scheme is more better in this analysis. So I divided galaxies into different set of analysts and then measure fluxes from each ring and perform SAD fitting again. And now I got some radial profile of individual galaxy physical properties. And then from the radial profile, I also focus on the spatial SSFR property. So I measure the power slope, which is the slope as a function of radius. So this is a similar quantity to the SSFR ratio that I showed previous slide. And then I got the key figure again. This figure shows the power slope of SSFR as a function of central mass density and total stellar mass at redshift 4, 5, and 6. So yeah, we have to be cautious to interpret this plot because this plot, the measurement of this plot is comes without K-band data, and at higher redshifts, it might be happen some kind of small number of statistics. So, but it's very promising because at redshift 4, from my statistical analysis, we got a similar result to the previous finding that I got from with K-band data. So the galaxies with high central mass density are more likely to have a relatively suppressed star formation rate near center, but it does not really depend on total stellar mass. And also, I try to analyze some radial profile, which is stacked from individual galaxies' radial profile. So I divided galaxies into two groups, which has a low central mass density, and the one has higher central mass density at different redshift park. And then by focusing on this bottom plot, which shows a specific star formation rate profile, all the galaxies at different redshifts have pretty much flat profile. So that means these galaxies form stars almost uniformly everywhere, but only for register 4 galaxies with high center mass density have a relatively suppressed subformation rate near center, which is pretty much consistent to the results that I presented. Yeah, so this is my summary. By utilizing the ground-based